All right, fellas, looks like we're ready to roll. Welcome back to another edition of Strength in Numbers, a webinar series presented by 1080 Motion. I'm your host, Adam Rolfe, and as always, excited to have our community gather again to make speed happen. Today's presentation will be an extension of our previous Coaches Corner conversation in February, as Adam Petway and Ola Eriksrud dive deeper into the numbers and speak about multi-directional speed in basketball, specifically assessment techniques. If you happen to miss the previous conversation, I do encourage you to check it out on our website, 1080motion.com. And under the Learn heading, you'll see all our webinars. Dive deeper into the understanding of how to apply power of the 1080 motion by checking out those webinars. We've had some since 2020, so we're excited to jump back into the Strength in Numbers webinars again. So let me introduce our panel. Adam Petway, Director of Biomechanics and Assistant Clinical Professor at the University of Louisville. And then our very own Ola Eriksrud, Associate Professor at Norwegian School of Sports Sciences and Head of Research at 1080 Motion. Gentlemen, great to see you again, and thank you for joining us.
Yep. Thank you for having us. Excited to do this. This will be fun.
Absolutely. And as we settle into things, just quick housekeeping, just remind the audience, you can ask questions, put them in the chat, the Q&A. I will lead the conversation in that part after the two gentlemen get done with their presentation. So we're going to kick this off. Ola, you're going to start, and then Adam's going to take it from there. So we're going to let you go. Thanks, guys.
Thank you. Thank you. I'm just going to share my screen here. There you go. I know I have a little bit of a glare in the background here, so sorry about that. But the content, what we were going to be talking about, is the most important component. So I'm going to jump right into it, and it's multi-directional speed, and this is a little bit of an overview. I'm going to kind of set the stage a little bit on test properties and how we thought about test development, and get into some KPIs and like how we look at data. And then Adam will take, I will pass the baton over to Adam, and he will take that conversation specifically into a basketball cohort. And then hopefully we'll have some time for discussions and outlook at the end there. So multi-directional speed, what are we talking about? You know, it's the ability to accelerate and decelerate in different directions. I'm not going to read the whole thing here, and I know it's a lot of words. But the point is that it's the ability to accelerate and decelerate in a three-dimensional space, you know, which is also one of the reasons why we call ourselves 1080. It's 360 degrees in three planes of motion. But one thing that I want to focus on here is the accelerate and decelerate component. So if we get into that, change the direction, accelerate, decelerate, I think it's also important that we do take that agility perspective into the mix here, so we understand what we're talking about. Because change of direction is more of the physical quality of being able to change direction, whereas agility takes that decision-making component, the mental piece, the perception action coupling into the mix. So when we're talking about change of direction, we're taking that a little bit out of the equation. Not a little bit, we're taking it out of the equation. Just so that is clear, because sometimes I read things and I see those things being confused. So deceleration is obviously a key component here, and from the animal kingdom, you know, basketball is less important than the life and death situation right here. But the point is that deceleration is a very key component in the animal kingdom, but it's also related to sports. So I thought the cheetah video here is kind of good to highlight that and some of the findings from there. And then if we look at change of direction, I think it's also important that we think about it from a horizontal context to a vertical context. And you know, historically, we've done a lot vertically. So our emphasis here is going to be horizontally, but we are not ignoring the vertical component. And if we go back, and this is where I provide a background of some of the models and some of the work that has been done, the foundation actually of where we are today and the foundation of what Adam is to be presenting, because historically we've had like a whole bunch of different exercises and that are used for different reasons, for different purposes. And what we have found in those exercises is that overall time has been used, and that continuous measurement is actually been a challenge. Rob? That has been a problem, because the continuous measurements allows us to see what's happening during the exercise and during the test. So getting phase specific information. That has been done, and they have, started to explore these things. And back in 2016, they started to look into this and seeing like, okay, I can get some continuous measurements. I can start to get into phase distinctions. I can start to get into understanding better what's happening during the test. And this has been an ongoing work. Here is Dos Santos and talking about the angular turns and demands associated with angular turns. And the shallower the angle, they call it more of a velocity dominant COD, whereas a steeper angle, 135 and 180, it's more of a force dominant kind of component. So to motorized resistance, some of you might be familiar, but I just wanted to bring it up so where everyone is on the same page. So because this is the technology that was used and employed in the study later. Motorized resistance technology here shown by both the 1080 Sprint 1 and 2. You can set up load independent of each other, concentric, eccentric phase. So let's call it assisted resisted phase. You can select how the load behaves, and you can also set speed settings. But in essence, how this works is that you have an engine. On that engine is a drum. On that drum is a line, and that is controlled by a computer. And we attach that to the athlete, and we attach it at the waist height with a pelvic belt. And when we do that, we can look at how certain variables, right? Here it's a video exemplifying velocity development during a test. We could look at force characteristics as well, but here is velocity. It's not perfectly synchronized, but the point is here we can start to look at phases. So, in black, we see initial acceleration and deceleration, whereas in orange here, we see the reacceleration, and we see the expression of velocity during these phases. So the first thing that we had to do in order to make sure that when we're doing these things and we're going out in the field, and that was a big thing here, being able to go into the field and into the applied setting to obtain meaningful data, we have to have an understanding of the validity and reliability of our data. So the first thing that we did was that we did this. We did this the same video that we did previously. We hooked it up to a number of people, and we had them do different COD tests. But the thing is that what we did is we had markers on them, so we can then monitor the center of mass movement, and then we could look at because that's the gold standard. Is the center of mass movement of the athlete, when I do all this, model and get all the center of masses of the different segments, and we calculate this and we compare that to the velocity that we obtain from the 1080 Sprint, is that valid? And the conclusion of this study is yes. So we checked that little box. So that's good. That's a good start. Then the next one to say, all right, so if I do this on multiple occasions, can I get reliable data? Are these measures repeatable? So I can trust them. And also, what are some minimal, detectable change, smallest worthwhile change? What are like change scores? If I observe these things left to right, or if I observe these things between athletes, or I observe these things within athlete, are these measures different? Do they represent a difference? So then we went into reliability. And when we went into reliability, we did it for a number of different tests. We did it for a modified 505. It's 5 meters in, 5 meters out. Then we did 10:05, 10 meters in, 5 meters out. And then we did 15:05, 5 meters in, and no, 15 meters in, and then 5 meters out. And then we said, well, can we start to look at output measures for like different phases of that movement? So we looked at phase, what we call the first phase here. We can call it phase 1A. That's what's used in the software, but it's basically the initial acceleration and deceleration, like velocity development, accelerations, forces, power, momentum. Can we look in the second phase, the reacceleration? And then we can dissect it even further, right? We can look at what is happening or how stable are the measurements of the initial acceleration. And the definition of initial acceleration is from start to your top speed or Vmax. Okay, do we have stable measures here? Very equal to that, decel. From that top speed to when I change direction of my speed. Let's call that deceleration. Then we can divide that into early and late deceleration. And one criteria that has been used and that was put forth by Harper and co-authors, was that we use a velocity criteria. And when it's reduced by 50%, we can look at early decel. And from that, we can also look at late decel. And then we can dissect it also from an acceleration perspective. When the 50% of the maximum is reached, early reaccel, and then late reaccel. So when we took all these data and put them together, we found that, well, it's reliable. And all of these data have been published. So we could check off that little box. And then we wanted to explore like what are some differences that happen when we do 5:05 versus 15:05 versus 10:05, because we wanted to see, are there like different traits associated with if I have a 5-meter approach speed, 10-meter approach speed, or 15-meter approach speed? So we looked into that, and what we did find then from a deceleration perspective was that in the shorter test, we found that the deceleration was greater towards the end of the deceleration for the shorter test, meaning the modified 5:05 versus the 15:05. So if you're looking at 9.7-ish here and 7.9 here. That also follows with force that was greater late for the shorter test versus the longer test. And this could be due to the fact that longer deceleration phase, distance and time, you get time to prepare. That said, you see that the impulse or the momentum that they're assuming is greater. That's not a surprise considering that they assume a greater speed. But the point here was to look at what are the demands that we are exposing athletes to if we do shorter versus longer approach speeds. The load set on the sprint was the same for all conditions. So that's important here. Moving on. And then we said, well, all the phases that we just showed you, that's a lot of stuff. That's a lot of stuff. It's a lot of variables. Can we simplify it a little bit? And the obvious answer is yes, because we can look at phase 1A, that is from the start to the turn. Let's call it initial accel to decel. Phase 1B, that's your reaccel. You have your Vmax, your top speed. From your top speed to turn, you have your decel. Then we actually went in and we said, based upon GPS data, we see that it's commonly used half a second interval to define maximum acceleration and deceleration. So we put that kind of criteria onto our data and we said max acceleration, the half a second interval with the greatest maximum acceleration. Same thing for decel, the half a second with maximum deceleration. And then we applied the same thing for the reacceleration, the maximum for reacceleration. So the data that Adam will be presenting is actually based upon your maximum acceleration and deceleration, these half a second intervals. And these will be reinforced, I know, by Adam. So here is just a case just to give it a little bit of life, a little bit of application as well. It's a left ankle sprain. Red, that's turn off your left. Blue, that's turn off your right. The red is the injured side. And if we start to look at some of the data from this, we see that the initial acceleration based upon the previous criteria is the same. The top speed is about the same. The phase 1A time, the initial accel and decel time is longer. And that is largely due to the decel time, which is longer, and the decel distance, which is longer, which in turn leads to a decrease in your deceleration on when I'm turning off my injured side, which also puts that into a rehab context. It puts it into a return to sport and return to play context. So I think it's important to keep these things in mind too, moving forward. And then in total, based upon your reliability, validity, we created a model for how we can start to think about change of direction. We have a start condition. How do we start? Is it an asymmetrical stance, symmetrical stance, rotated stance? In what direction am I moving? What kind of locomotive pattern do I have? Because this is a model that we used for this test selection and what Adam is going to talk about. And then you have angular turn, the transition point. We used horizontal, and it was a 180-degree turn in that case. And then when we come back in here, we can look at directionality, like in which direction am I moving? Is it forward, backwards? And what is the locomotive patterns? And this kind of perspective allows us to put literally any kind of movement into the mix. And we have explored this, and we did this in football, and we decide based upon ecological validity or the kind of like the speed that the athletes are assuming during soccer. And we used this model, and we said, all right, we're going to use a 15-meter approach. We're going to use a 15:05 to look at change of direction in football based upon pressing speed. And then based upon that would probably not be the best thing to do if we're looking into basketball. So that's where we went with shorter distances because it's a more confined environment and a smaller environment. So I'm going to pass the ball. It's not the final shot. I will return
Nice.
and support the discussion after Adam is done with his stuff.
Nice. Great assist, Ola. I appreciate that. Yeah. So, based on a lot of Ola's work, and I think the impetus behind this project actually started this summer in Prague when we presented to the EuroLeague coaches. I got to see Ola present. He saw my presentation on basketball mechanics, and we kicked a lot of really good ideas. And what we came up with is basically, we couldn't find any kind of multi-directional deceleration as far as it relates to standardized and repeatable protocol in elite basketball. My background, I spent 15 years working in basketball. Ola has a background in basketball. So, based on our collective efforts, we just wanted to understand in elite basketball, what does deceleration qualities look like? And what does the distribution look like based on, position, training age, level of competition, things like that. So we got a really good research group. It's myself, Ola, and then Damian Harper and Daniel Cohen from the UK. And, we just went on site to 10 different Power 4 NCAA basketball teams. So it's myself, just standardized and repeatable in the data collection, and one of my graduate assistants, right? So the studies we did just based on Ola's work, we wanted to do some sort of, horizontal deceleration. So, 5-meter entry with ADA, horizontal deceleration, increase the entrance distance and distance velocity, 10-meter ADA, 180-degree turn, so a 5:05 with a right foot turn and a left foot turn. And then I think this is where the level of specificity kicks in as it relates to the sporting activity of basketball is lateral shuffle. So when you look at a lot of the research, I mean, there's a lot been done on horizontal deceleration, a lot on change of direction in 5:05, not a lot of frontal plane assessment, right? So really, when you look at there was a great paper by McGinnis and colleagues in time motion analysis, and he found that, athletes in competition spend around 31% of the time in shuffling movement patterns, right? So, particularly on the defensive side of the ball, it's a very important movement pattern in basketball. So we really wanted to kind of hone in and look at lateral deceleration as well. So we went on site, 10 different teams. There was 124 different participants, elite level of Power 4 NCAA basketball. The distribution of position, there were 70 guards and 54 bigs, right? So going through the tests we used, we did obviously start position. It was a self-selected start for the 5-meter ADA. There was a 5-meter lead in, and we had 5-meter segments for 15 meters where you broke the 5-meter plane, right? Decelerated and backpedaled back to the 5-meter mark, right? So here is an athlete performing just a 5-meter ADA right here. So you can see initial acceleration past the 5-meter mark, backpedal. And we demarcated those 5-meter segments just with an orange cone and blue painter's tape. So right here is a 10-meter lead in, right? So just increase the entrance velocity and the entrance distance. So again, self-selected start, sprinting through that 10-meter mark, right? And then decelerating and backpedaling back to the 10-meter location. So right here, same athlete performing 10-meter lead in, initial acceleration, decel, backpedal, back to the 10-meter mark. So 505, again, select starting and finishing in the same position, self-selected. So typically a stagger stance, they could pick, right or left foot lead based on preference. Sprinting to the 5-meter mark, 180-degree turn with both we did one trial with the left, one trial with the right, and then sprinting back to the starting position. So right here, you can see staggered stance start behind the start line, 180-degree turn with the right foot, and we did both right and left foot. And then for the lateral shuffle, you're perpendicularly oriented to the 1080 machine, and in all tests we're going into the 1080 and out of the 1080, right? And then you shuffle to the 5-meter mark and then shuffle back to the starting position, right? So right here, pushing with his right foot to translate left, 0 velocity, then pushing back with the left to translate to his right laterally. Right. And so what did we find? Right. So we found there's a lot of different components in different phases to the entry and exit, but this point of 0 velocity, center of mass 0 velocity, when they were changing directions to orientate back in the opposite direction, was really important. And what we found is there were some positional differences relative to this 0 velocity position. Right. So these are two bigs, right, classified. What we found was at this change of direction moment, both in lateral and both in the 505, like 180-degree turn, they used a strategy of bigger stride length, right? So a big wide base and more of a medial trunk lean, right, for the bigs, right? So they really tried to use their size. Think about getting out and hedging ball screens, or like really trying to use their length to create advantageous positions at the point of 0 velocity, right? And they did this with wide stance and medial trunk lean. Now, this kind of deferred based on the group relative to the guards, where we saw the guards took shorter, choppier steps with shorter ground contacts, but really got into greater degrees of hip and knee flexion at the point of 0 velocity. So a little bit more narrow of a base based on, anthropometric measures and limb length, but they really got into deep degrees of hip and knee flexion, right? So different strategies based on different positional demands. This is really, these phases we found to be really important, particularly in the 505 of just this, initial acceleration as you get out. Obviously, you're going to hit your top speed around like 2.5 meters. There was a deceleration zone, a point of 0 velocity. And then upon the 180-degree turn, there was a reacceleration in the opposite direction. And then, a second top speed in that second 5-meter segment, as Ola mentioned, right? So what does that look like, in real time when you pair it with the film, right? So there was an initial overcoming of inertia during that, acceleration, right? And the gradient of that slope is just a acceleration max and the half a second time integrals, as Ola mentioned, right? There was a point of top speed in 1A. And you notice, the trunk became a little bit more vertical and the shank angle became a little more negative with a heel strike to create braking horizontal forces in anticipation for that zero velocity moment, right? And then the athlete would hit zero velocity upon like turning to head back into the opposite direction, and then would reaccelerate, right? To run back to the starting position in the second 5-meter segment, right? So within the ADA, we wanted to kind of look at the same thing. So 10-meter lead in, right? So there's an initial acceleration zone, right? So there was the initial overcoming of inertia. And again, just acceleration mechanics. This was usually the first 3 steps in the 10 meters. And the approach, you could see initial overcoming of inertia. There's a forward trunk lean. There's a, almost vertical shank angle and a gradual rise of the center of mass during acceleration, right? There was a point of peak velocity, usually around the 5-meter mark, right? In a 10-meter ADA, so about at the halfway point. And then you notice the shapes start to change as they want to go from the acceleration zone to the deceleration zone. So more of a vertical trunk or even more of a negative trunk lean, right? You could see that obtuse or negative shank angle upon ground contact and a very rigid heel strike and actively dorsiflexed ankle, again, to create larger magnitudes of braking horizontal forces within the deceleration zone, right? So as, they hit that top speed, then that back half of the 10-meter deceleration, you could see obviously casting outside of the center of mass, a lowering of the trunk and center of mass, and greater degrees of knee and hip flexion upon ground contact, right? So you can kind of see, looking from left to right, just acceleration, the first 3 steps, a rise of the center of mass, hitting peak velocity, and then a gradual lower center of mass. So it's really, the x-axis is just position right there, up to 10, 11 meters, and the y-axis is just speed in meters per second, right? So you can kind of see the shapes change from each segment of the phase of a 10-meter deceleration. I think this is really a good visual just to show you the different phases of what that looks like within this movement pattern. So the lateral shuffle. So the entrance velocity on the lateral shuffle is obviously a lot slower than your 505 or 10-meter ADA, because you can translate horizontally faster than you can in the frontal plane. But typically what we saw with our guards, it would take 3 to 4 steps to cover a 5-meter ground, right? Bigs would be bigger steps with longer ground contacts, usually doing it in about 3, roughly, right? So again, if I'm leading with my left foot, I'm pushing against the ground with my right. Equal opposite reaction is going to translate my center of mass in the opposite direction, laterally going to my left, right? So pushing off the right to go left, pushing off the right to go left, pushing off the right to go left. Typically 3 push steps would get the guards 5 meters. Sometimes it would take 4, just depending on limb length and depending on ground contacts, but that was typically the ranges. You hit that point of zero velocity when you're changing directions. Equal and opposite, you drop the center of mass, and now I'm pushing with my left foot to go back to my right. So pushing with the left to go right, pushing with the left to go right, pushing with the left to go right. Again, so this is a guard, so shorter ground contacts and shorter stride length. If this was a big, the hip abduction velocity and the stride length would probably be bigger with greater ground contact. So again, based on anthropometric measures and positional demands, we saw differences between our guards and our bigs within each test, right? So then we just wanted to look at the average of each. So we took all 6 tests and we looked at decel max, total time, top speed, and accel max and decel time, just based on the time points from each movement, right? And we just wanted to look at positional norms and just look at the distribution of data within each test, right? So right here for the 5-meter ADA, right? So you see your initial acceleration zone, and that's where you get your acceleration max. You see that green bullet up at the top right there, about 6 meters per second, and that's where we get our top speed, right? Then you have your deceleration zone where you get decel time and decel max. And the aggregate of acceleration and deceleration was your total time, right? So same thing with the 10-meter ADA, and obviously with an increased distance, you're going to increase your top speed and you're going to increase your entrance velocity, right? So there's the acceleration zone, top speed, deceleration zone, right? deceleration time, and the aggregate of the two is the total time. Interesting enough, right? And we want to point this out because it's kind of a imperfect right now. We're still developing this, but I could tell if you're, maybe watching this at home, you say, well, Adam, the team, right? So the team is, de-identified there on the left. The team, and it's ranked based on deceleration max of the 10-meter ADA. You could see the team at the top, right, that had the largest deceleration max also had the largest time to completion. And what we found is just based on increasing the entrance velocity, you also increase the deceleration zone. So meaning if you're coming in very quick, it took you a longer distance to decelerate and backpedal back, right? So the time to completion was greater. So again, something to consider if you're just using time for this and not using any kind of motorized resistance, you wouldn't know that, right? So again, when you're kind of piecing the puzzle together, it's good to have kind of all the metrics and all the variables, available to kind of ask more questions or maybe layer your assessment with a little more depth. So 505, right? So same thing. So Amax 1, we got that right and left foot. We got the top speed from this particular test. We got the decel max and the point of max deceleration and deceleration time. And then the aggregate of both 5-meter segments would give you your total time, right? Of note from this, and what I thought and Ola thought was very interesting is that the deceleration max across the board from the 505, and Ola mentioned this earlier based on entrance, distance, and velocity, was consistently greater than the deceleration max of 10-meter ADA, right? So the decel max on a 180-degree turn, even though you're entering at 5 meters, was consistently greater than that of a 10-meter just deceleration task, right? So again, just kind of layering the depth of your assessment. And then lateral. The main thing here is obviously in the frontal plane, you can locomote with a lower velocity than you could horizontally, just accelerating, right? So your top speed was less than your 505. Therefore, your total time was greater. So then we wanted to look at the data by position and just look at all the different metrics from the 505, right? And just looking at effect size between groups, what we found is there was large magnitudes of effect size when looking at top speed 1A and deceleration max when comparing bigs to guards. So guards consistently outperformed the bigs within this task. And when you look at the positional demands of basketball and what guards are asked to do on the perimeter, this makes sense. And when looking at body mass as well. So now what we wanted to look at is just using time as our outcome measure in the 505 and as our dependent variable. We wanted to look at how do all the metrics that you can gather from the 1080 associate with total time. And what we found was your ACEL max 1A, so just your initial overcoming of inertia, and your decel max in that first phase had the strongest association with lower total time in this cohort, right? So just getting out quick, using a pacing strategy, and rapidly turning on the brakes were the most important segments and had the strongest association with lower total time within this cohort. So now with our lateral data, we just again wanted to look at positional differences. And what we found is, again, going back, decel max, right? So decel max had the largest effect size as it relates to differences between guard and bigs when looking at that lateral 5-5 shuffle test. So then what we wanted to do is run a split analysis. So we wanted to compare what does a high versus low decelerator look like as it relates to a 10-meter ADA, right? So we just split based on position, high decelerators versus low decelerators. And we compare that to our lateral shuffle data, right? So when looking at horizontal versus lateral, right, we took our high versus low decelerators in a 10-meter ADA, and then we just compared it to all of the metrics that you can obtain in a lateral shuffle. And what did we find? decel max had the strongest association in a lateral 5.5 as it relates to splitting high versus low decelerators in a 10-meter ADA, right? So what can we say from this? If you are good at decelerating horizontally, then more than likely you're also going to be good decelerating laterally. Not in all cases, as we'll see later, but when you look at the totality of the group and split the group based on position and high versus low decelerators, this is what we found. So a couple of case studies here, and I think this is really interesting. When we were putting all these tests together, Ola made a very poignant comment that really resonated with me. And he said, if your best athletes aren't grading out well in the test you're using, you may not be using the right test, right? So this is just a case study from one of the bigs in our cohort, averaging currently 19 points and 11 rebounds, and is the front runner of the player of the year. So you can see the red bar going vertically is just the positional averages across college basketball, where the black bar is just where he fits relative to the positional norms, right? And you can see in the 505 left and right, he greatly outperforms his peers. In the lateral shuffle, same thing. However, he is just average in a 10-meter ADA, right? Well, why is that? It could be a tactical thing and how they use them. It could be, biased towards certain directions or certain tests, but just something that kind of stood out. I mean, this is a very high-level athlete within college basketball. And, he was just average relative to his peers in the 10-meter ADA. So here's a second case study that we looked at as it relates to an All-American point guard. Leads the country in steals, projected All-American. He was last year in the 23-24 season, defensive player of the year within his conference. And as you can see, he's just a good mover, right? We should, mention that we also did vertical testing on the force plate and did a myriad of different tests. And this athlete is good vertically as well. So you could just tell that this athlete just outperforms his peers. And relative to knowing this athlete's anthropometric measures and body mass, he's short, compact guard, and needs to move well in all directions, right? So his strength is just being able to move in all planes of motion upon all axes, right? He's significantly better than the positional average of all of his peers. So he's just a really elite mover. So this one we found really interesting. So freshman, big, right? Averaging 15 and 6, projected NBA lottery pick. And you can see laterally, he's great. I mean, he can switch probably 1 through 5. They use him defensively on the perimeter. He can really move his feet well for, an athlete that's 7 feet tall. Changing directions, right? So he's a pick and pop big, not a traditional big, can do a lot on the perimeter. So he's really good at 505 left and right. But when you go down here and you see his ADA performance, he's actually significantly lower than the cohort of his peers based on position, right? So why is that? Maybe he's not your traditional rim running big. So it could be a tactical thing, could be training age. He's 18 years old. So he may not be familiar with those types of lead in, velocities or deceleration capabilities. But again, something that's interesting. And the fact, you could be good at one test or one direction, but that doesn't necessarily mean you're good in every direction for each specific athlete, right? So very interesting case study right here. And just thank you to 1080 Motion and Val. Our research group was really solid. Thank you to all the coaches. I mean, the coaches were all very, very gracious with their time and very hospitable during this process. And if you'd like to find out more on this topic, this is kind of like a prelude to Ola and I will be presenting at the Basketball High Performance Symposium, May 8th and 9th. And we're going to kind of take a little bit deeper dive into some of these topics.
Thanks, Adam. Thanks, Ola.
Thank you. Yeah.
Awesome. Okay, we have some questions that came in. I have some questions as well. You guys always get me thinking. So first off, let's talk a little bit about the 1080 using the forces. And when looking at data for deceleration and reacceleration, maybe this was for Ola more than anything. Do you value total output of force per each phase, your 1A, 1B, more or rate of force development. So really just looking at total output. Do you even look at forces when you're looking at the data for COD, deceleration work? How do you manage that?
That's a good question. I think we've been more focused towards getting kind of like an overall sense of what's going on. And by that, I mean you're looking at how do they like what's the magnitude of their deceleration, which in turn is reflective of the force they are generated. But I think moving forward, it's certainly interesting to dive more into the force data and the slope of those force data and then getting step characteristics into it. But I think as a first step to start to understand this, and also like Adam was saying, like if we're doing these tests, they better reflect and be able to differentiate. And I think the last three cases there have like an interesting case here, you know. If we're starting like a little broad and a little bit more general, and we're seeing that we're barking up the right tree, kind of like, okay, we're on to something here. I think that is the evolvement of this moving forward. But because if we came back and we're like, well, this doesn't add up, you know, it's like the best guys are below average or average. That doesn't make any sense, you know? So I think that would be, you know, steps as we move forward for sure. But the directionality of it, I can pop up a little slide later on it, but the directionality and being able to look at multiple directions and see how your athlete performs at a little bit more global level, I think is incredibly valuable at this point. And it's like Adam said, very little is done. So I think this is kind of like our first step, you know. Did we do mistakes? Absolutely. Would we have changed things up? Yeah, we might change, you know, we'll change things up moving forward and then we'll explore different things. I don't know. Did I answer your question, Adam?
Yeah, you did. And I think that's a lot of times when I'm working with people with their 1080s, we don't talk a lot about force output with the assisted or resisted directions. Um, I think there's other metrics that you guys are looking at closer.
Yeah,
One thing to clarify, on the testing with the 1080, you use 3 kilo assisted and resisted. Is that correct? Okay.
yes.
Correct. Yeah. Standardized resistance. Yes.
Standardized for that.
And one of the reasonings for doing that is that we have established that as, you know, used that historically. Also, going on that kind of loading allows the athlete to self-select rather than pulling them very hard, so they can to a greater extent self-select without like, whoa, what's going on.
Mm.
Also, it's a safety consideration in that, you know, when you go into a new environment, you're doing these tests, you know, these are very benign loads, they're very low loads, so they're safe. So we went safety first, for sure.
Okay, so I'm the simplest reductionist on the team. So I'm always thinking, okay, you guys got some awesome tests here. I heard Adam say, hey, we know if somebody does a horizontal decel test, that usually translates to something as well as probably a pretty good person in lateral direction. Uh, Coaches are always busy. We know that. For testing, there's a lot of things to assess, jumps, linear sprint, multidirectional now as we're talking about it. Did you, after doing this and we've learned some things, what are the tests that you would encourage people now to really dive into? Like, what are the ones that are the most meaningful? And is it different between guards and bigs? Maybe I didn't catch that. Should we be having different protocols for those types of athletes?
Yeah, I think that's a good question. You know, Ola made a good point about being ecologically valid as it relates to your testing battery, right? Obviously, time is always a constraint, you know, in an applied environment. I think I would have an initial battery, but I think I would actually look at it more integrating a lot of the testing into training, right? So like having some sort of entrance velocity based on, you know, what speeds you can achieve, maybe relative to body mass or relative to position, and just start training that, whether it's like you know, a 5 meter lead in to a 505 change of direction, 10 meter lead in to, you know, going back to the 5 meter mark. I think all of that is at play, just depending on what you're trying to accomplish. what I would also say within that is, and going back to, is there one test better than the other? I think layering your tests with, multi-direction is really important, because just because you're good in one direction doesn't necessarily mean you're going to be good in the other. If there was something we could change, and like, we did make a lot of mistakes, as Ola alluded to. I think, 5 meters is just a ton of different distance to shuffle laterally in basketball. You never really do 3 consecutive shuffles before, if you're the primary defender on the ball handle, they're going to change directions. They're not going to, dribble laterally for, a 5 meter segment. So maybe looking at testing battery in the frontal plane, whether either it's more like reactive agility, as Ola mentioned earlier, or it's self-selected, meaning like you look at contact time and distance relative to a truncated, like, okay, you're going to do 2 shuffles, and we'll measure how quickly you shuffle and how far you shuffle and how quickly you can get back to the starting position. So I think, maybe toggling with that 5-5 lateral shuffle is something we may build upon in the future. But I think just as a baseline, and the fact that, not a lot of people are looking at it and are studying it. And as mentioned, 31% of the time motion analysis was found to be in the frontal plane. I do think it's important relative to the sport of basketball. I just think maybe we need to keep toggling a little bit with, the methodologies behind that test. But I wouldn't say one is better than the other, or looking at, this test is the only test you have to do. I think maybe layering and having your needs analysis very deep, and then that will paint a picture for what each individual athlete needs. And then you can kind of incorporate, what, your training looks like based on their needs analysis, right? So yeah, I don't think necessarily like one is better than the other. I would say, have a robust analysis that you maybe do quarterly, and that will kind of dictate your interventions based on what you see as far as what they perform well in, but probably more importantly, what are their deficits based on these specific directions.
Yeah, no, I could not. I'm going to share my screen on. I'm going to pop one slide up here. Here's a little bit of a heat map of a team, right? And you have different athletes, and I always get these questions. Well, testing should be short, and then my reflex. Well, it's always like, okay, it's always good to know where you're at, because it's like a GPS. It's like if you know where you're on the map, you have a better sense of where you need to go, right? So, and then that's where, I totally agree with you, Adam, like integrating that into quote unquote invisible monitoring, where you can obtain these for like over a period of time, certainly is good. So here's an example, linear sprint. So you can see how certain individuals, number 3, across the board is in the green, right? Here you see another, he's more yellow, and then it turns red, excuse me, when he's going lateral. Here you have it, number 7. Here you have red numbers for deceleration, regardless of direction. You get these kind of intel, you get these kind of information, stand out pretty good. Whoa, what's going on here? Going to his right, pushing off. What is happening there? Like, why is that? It raises questions, and I think that could be very valuable from a performance, strength and conditioning, but also going back into rehab. And having these baseline measures, we haven't even talked about the continuous data. I showed it a little bit on the ankle sprain case, but having these continuous data and look at them, they are almost like a fingerprint. Having that as a reference, if they get an injury, say an ankle sprain, going back at it, it's like, how has this behavior changed? And adding that to that return to play, return to sport argumentation or a piece of the picture, I think is extremely beneficial, in my humble opinion. Again, number 12, what is going on here?
Right.
It raises some questions,
Okay, let's jump on that. So we got a question here from Ryan that says, awesome information. Are any of the tests particularly sensitive to identifying those asymmetries due to a current or a previous injury that you guys were doing? Or is there something you would advise people to use?
and that is
You all
where
know.
and this is where reliability comes in, right? Because if we have those reliability data, we have, okay, so if you're doing this kind of variable, we know that the smallest worthwhile change or a moderate worthwhile change, that's this magnitude. If that magnitude is different and we have stable data, we know that, say it's a 0.2 or 0.3. I'm making up numbers now. But if that magnitude, if that is outside that, we know it's different. And then it could be, well, you have a person who really likes going that way, or he has a very stiff ankle on that side. He can't get into positions. His hip is not able to open. You get into these kind of conversations. So I think using repeatability measures and knowing what's different, then you can make an inference and saying, well, it's different going left and right. No wonder he cheats over to one side when he's going to defend the ball. It's you're getting into conversations with coaches that I think could be extremely valuable. I'm sorry if I deviated off your question, Adam, there, but
When you look at athlete number 7 on your
yeah.
presentation, okay. So when I see that and I see the red on deceleration, and deceleration for this guy or this
Yeah.
person, what? And I know we're talking mostly assessment here, but what does that? And we say potential. He can get better.
Yeah, I like
Is
I like
that
to call
is
it
that
room for improvement.
room for improvement? But are we worried about, like, this person clearly doesn't have the brakes, it looks like, right?
Yeah,
Is this a higher
yeah.
injury risk when I see that? Like, is that what we're trying to tell people as well? Or is it
No, we don't have data to say that.
okay?
This is now I'm putting on my scientific hat. We don't have data to prove that by any stretch of imagination to say that, well, that's an injury risk. And
Mm.
also keep in mind, this is within team comparison, right?
Okay.
So if I'm using a within team comparison, uh, his deceleration values compared to another team could be really good, right? So this is where data is very, very valuable. I'm not saying that that would be an injury risk because I don't have any backing for making that claim. Now, that said, compared to his peers, and also we don't have info on number 7 here. I'm not telling you which position he is. Is it okay? That's that big guy, that's okay. All right. He moves, you have to put those things into the context, right?
Yeah. Okay.
So you're painting it. It's like Adam, I totally agree with that visual. It's painting a picture and facilitating crosstalk, communication, dialogue between different, you know, staff members, whether that is the athletic trainer, performance coach, strength coach, physio, or the other coaches, assistants and head coach. This is where my goal, if I'm a coach, my goal is to create queens. I'm always using the expression from the chessboard. I want to create queens. I want them to be able to excel and decel in all directions. I don't want peasants when I'm setting up my chessboard. If I can select the pieces that I wanted, I would have all queens. So my goal is to create queens.
Okay, so I'm gonna piggyback on that because Adam, you said there is a sweet spot when you're looking at the data for someone that's accelerating basically at the right pace to decelerate fast. Some guys
Right.
accelerate too much and then they're really slow decelerators. Can you? Okay, so that's, to me, that's the queen, right? Like, that's the person that can do that really, really well is the one that shows that they're green in those metrics on Excel and Decel. Uh, and I'm going to go off the assessment tactic a little bit, but what did you see in those patterns that someone could do that well? Like, what is there anything we can glean that you were like, that made that person special? They got it, where someone else just didn't even understand the motor control of how to go. They went too fast and they went too slow.
Yeah, so that's a good point, Adam, and a great question. I think rarely did we see somebody that was a horrible accelerator that could all of a sudden flip on and just turn the brakes like rapidly, right? So being in good positions as you overcome inertia and being in good positions for acceleration, as far as, like, trunk lean, shank ankle, ground contact, how you coordinate your limbs in space as you accelerate. Typically, if you're in a good position in acceleration, you had the bandwidth to then, okay, like have a posterior trunk lean, change direction as far as like your shape and limbs and coordinate it in space, cast the shank a little bit, heel strike, and kind of reverse the mechanism of acceleration, right? So I think as just because you're a good accelerator doesn't mean you're going to be a good decelerator. But I do think, just in observation and seeing these 154 athletes, I think it is a barrier of entry, right? We never saw anybody with horrible acceleration mechanics just all of a sudden just become a great decelerator on the back half of a 10-meter ADA or a 505. Or just like, hey, you don't understand how to, push laterally against the ground to get an equal and opposite reaction to translate your center of mass laterally in the opposite direction, right? So I think in context and how you coordinate your limbs when you accelerate isn't going to make you a good decelerator, but I do think it's a barrier of entry to being good at deceleration, right? So I think having a good foundation of acceleration mechanics is very, very important as it relates to deceleration.
That's good. I think that's really interesting because I talk a lot with other sport coaches, and let's say football, American football, we talk a lot about speed, speed, speed. And we don't talk a lot about, okay, but how well do you decelerate, right? To Ola's point right at the very beginning with the cheetah, and we still have to decelerate in most sports to create space. But it is interesting that you said like, hey, it's actually probably okay to say, hey, you need to have good acceleration mechanics that's also enhancing your deceleration. So you may make that a focus, but that's actually like part of a comprehensive plan.
Yeah, no, absolutely. I don't think again necessarily one is better than the other, but rarely did I see anybody that was horrible in acceleration and then all of a sudden got in the right position to decelerate, right? I think it's again almost a barrier of entry. One kind of feeds the other.
Nice. We got time for one more question, Ola. This is going to go back to your heat map. So if you want to pull that up for a second. The question is, so how do you determine the reference for potential average and elite? So within this cohort on this team, did you just give a brief overview of how you did that?
It's a great question, and I think I alluded to it a little bit too, because this is purely based on within team averages, right? And then basically z-scores and how you break down relative to your own peers on that team, right? So I think as we accumulate more data, and I think it's been a very valuable start. It's been a good starting point to try to get at least some sort of criteria, some sort of measurement, and kind of validate it. I think the cases with Adam at the end there, the 3 cases there, are very, very interesting to see. Like, we are now starting to look lateral. And then we can argue, well, it's too long, the 5 meter. And I totally agree with Adam. But the problem with if we give them an open task, right? I just want you to do 2 steps back and forth as fast as possible. What's going to happen is that they're going to do 2 very short steps, and it's not going to be what we want. So it's I think moving forward, establishing more data so we understand it, looking at different levels, branching down, like this is also male, female population would be very important. Going into, say, high school level or other level. And this is where we're thinking about moving forward, among other things, both Adam and myself, to like, are there other teams, other places, get the female population involved, doing some refinement of it. But the values as it stand right now, that was a long-winded answer to a very simple question. It's within team right now, because that's what we have. That's what we have. And these data, we will write up different stories that will be published. So just keep your eyes open. They will come, they will surface, and they are there to be used. And that's why I also like to publish like a whole bunch of data, and people say, well, this is just cross-sectional stuff. No, cross-sectional stuff is interesting because then I have something to relate my data to. I can put some sort of context on them. I don't know if I answered the question. Sorry.
You did great. You did great. Ola Eriksrud, Adam Petway, thank you very much, guys, for your time. Thank you, everyone, for your attention today. We value that greatly. And hope everyone has a good end of their day. We're going to wrap this up now. So signing off. Thanks, guys. Adam Rolfe, 1080 Motion. Make speed happen. Talk to you later.
Thanks, guys.
Take care.